Hi, welcome back to our the next session of the moving charges and magnetism. Now, when we talk about moving charges, till now we talked about the force that basically what is the kind of force, the magnetic force, how does it look like, F magnetic and F electric that we have seen. Now, when there is a motion that is happening inside a magnetic field, how the charges move. So, let us take a little bit of it is the first step is to see how the force is applied, what is the direction of the force. Now, what does the force do for the movement? So, we will look at that in the magnetic field. So, what we will do is, let us first consider a scenario, okay, where there is a magnetic field. The magnetic field is somewhat like this. So, when I have put crosses here, they actually mean this is magnetic field is perpendicular to the plane of the board and going inside. So, that is basically these crosses. Now, what I will do is I will actually take one charge, okay, one charge and put it here, and that charge is, let us say, plus q. Okay, when the charge is plus q, and let us say the charge has a certain velocity in this direction. This is the direction of velocity v of the charge. Velocity is in this direction. Now, what will happen if there is a velocity in that direction? So, if you see carefully that we have written F is equal to magnetic part is equal to q into v cross p. This is the direction of the force. So, let us say plus q, so q is positive, and v cross p. V is this way and b is inside. So, when we do a v cross b, what will happen? So, let us just look at that part. So, this is basically the direction of v, and this is the direction of b. So, I am just turning it like this, okay, v and b. So, v cross b, when you do, it turns like this. So, when it does like this, so the force, what is the direction of the force? So, sorry, this is v, you can see here, this is v, okay, this is v and this is b. So, v to b, when I go, v cross b means it comes this way, okay. So, that way is nothing but the force in this direction. This is the direction of the force. So, you can very clearly see the direction of the force is towards left side. This is the direction of the force. So, see, think yourself once again that we are doing v cross b. Whenever we do v cross b, this is v and this is b, v cross b, turn it around like this, and you get your screw this side, or the pipe, the bottle cap comes this way, okay, outside. That means in this direction. So, just do some little bit of practice on this bottle cap and the screwdriver and screw and things like that, to know exactly when you turn it which side it moves, okay. So, F is like this. Now, the second one, let us say when that happens, you can see that it actually bends. It is, look at this, F is actually perpendicular to V. When there is a force perpendicular to velocity, then it does not change the magnitude of the velocity, it only changes the direction, okay. So, it changes the direction of this velocity, and let us say it keeps going like this in this path, and it will go into, let us say, another point. In this point again, you can see that the velocity actually will be in this direction, and if the velocity is in this direction, we can very clearly see v cross b will be actually in this direction again. So, at every point that it travels, goes around like this, let us say the v is again in this direction, this is v, and f will be in this direction. So, you can very clearly see it is actually tracing a circular path like this. All that time it is basically going around a circular path. So, if you are having, if you just leave a charged particle with a certain velocity, like this, perpendicular to that, and leave it like that. So that charged particle will be continuously going around and round and round for a long time. So why does it go around? Because the velocity, okay, the magnitude of the velocity does not change at all. Only the velocity of the direction of the velocity changes, and it takes a circular path. And you can very clearly see that in such a scenario, this is basically what we call centripetal force, okay, which has a radius, let us say r. This has a radius r. This is a centripetal force, and you can see that the work done by this force. What is the work done by this force? Work done by the force is always force into displacement. Displacement in the direction of the force. You can see here the displacement will of course be there, but it is actually never in the direction of the force. There is absolutely no component in the direction of the force. It is always perpendicular to the direction of the force. Therefore, work done by a centripetal force, as we know, is always 0. There is no work done. Okay. Since there is no work done, we can also say that there is no change in energy. So there is no change in kinetic energy at all in this. You can very clearly see. So because the velocity, magnitude of the velocity, kinetic energy is half mv square energy. So this is going to remain constant, half mv square. Okay. So that basically is the crux of this scenario. Okay. So whenever you have a magnetic force, magnetic field force, magnetic field you can say is basically causing the moving particle to experience a force. That force never does any work on the particle. Okay, that we have to understand that. So in no so it's always going in a circle. Now you can always calculate actually the value of the r. Okay, it's easy to calculate value of this r. What is the radius of this circle? How much is the radius of the circle? Let's calculate. Okay, so we know that the force. What is the value of this force? Force is equal to Q into VB into sin theta. So sin theta is sin 90. Okay, I will not write it. Sin theta, sin pi by 2. Okay. It is just QVB. Pi by 2 is the angle between V and B. So similarly, we can say because of this works like a centripetal force, we know the formula for centripetal force also from mechanics. So centripetal force is actually is equal to mv square by r. So we can equate these two. This is the centripetal force. Therefore, mv square by r is equal to qvb. So we can say in that case r actually is equal to r, if you go this side, mv by q into b, mv divided by q into b. That is the value of the radius. So one can actually easily calculate the value of the radius by looking at what is that dependent on. The value of the radius depends on the field, that is the electromagnetic field. If magnetic field is very high, the radius is smaller, which means basically it will turn very fast because there is a lot of force. Okay. So a small radius, and if the mass is high, again it is a big radius because it is having inertia, it is difficult to turn it around. So velocity is also same thing. This is basically the momentum. Okay, if momentum is high, it is hard to turn it. So radius is higher. Okay, and Q, charge. If the higher charge, then lesser radius. So this is basically the radius that we want to, and you can see that this radius, okay, is dependent on, okay, velocity and dependent on b, these values. Now let us just look at one more thing. Okay, the radius is fine. So what about, okay, is it possible to, let us say, find out the time duration for going around? Okay, let us say frequency. Okay, what is the frequency? Okay. So we know that R is equal to mv by qb. Okay, so we can calculate also V is equal to, we know, omega r. V is equal to omega r. Okay. If I substitute that here, then you can get R is equal to m into omega r by qb, which implies omega actually equal to qb by m. So what is the meaning of that? So omega is nothing but 2 pi into frequency. That means basically this implies 2 pi into frequency. Frequency I will write it as nu. Okay, frequency. Here you can write f also is equal to qb by m. So that means, okay, you can see very clearly that nu is equal to, that is frequency is equal to q into b divided by 2 pi into m. And we also saw R is equal to, I am going to write some of these things because it is very regularly required, mv divided by qb. These things you can actually derive them whenever you want, and if you have a good understanding of what we are talking about. So what we are saying basically is the frequency of this going around, which means 1 by t, or even the t. What is t then? This implies t is equal to 2 pi m by qb. This is inversion of this. So you see that t or nu, that is frequency, is independent of the velocity. It is not dependent on the velocity. You can see very clearly here, there is no v term here. How much ever is the velocity, okay, the t remains same. So that's a little surprising if you look at it. Whatever may be the velocity, its frequency remains same. It takes same amount of time to go around one round. Suppose if you increase the velocity, what will happen? If you have a higher velocity. So if you have a higher velocity to start with itself, okay, then it will actually take a bigger circle. It just increases the radius of the circle, because radius depends on v. And when it increases the radius of the circle, accordingly it also basically makes sure that it takes exactly same amount of time again. So the frequency is always dependent only on the b, m and these two values, qb and m values, and not at all dependent on the velocity, a particular velocity of the charge. Okay, so that information is very crucial for us. We are going to make use of that information, that it is basically having same frequency. So to build what we call cyclotrons. Cyclotrons are the equipment which can be used to basically accelerate the particles. If you want to accelerate the charged particles, either electrons or ions, any of these particles, when you want to accelerate, you can get them to very high speeds, because you want to bombard them somewhere, you want to use it for some ionization, you want to create some new elements. In all these times scenarios, you want to basically be able to accelerate some of these charged particles. So cyclotron helps you do that. So in building a cyclotron, we use this important feature, which is whatever may be the velocity, even at a higher velocity, it actually takes same amount of time to finish one round. That is the beauty of a cyclotron. So before we go into cyclotron, I will actually see also one small aspect of this. So the velocity we have taken here to be actually exactly perpendicular to b. Okay. We have taken velocity to be exactly perpendicular to the magnetic field. You can see here, magnetic field is in this direction towards inside, and velocity is in this direction. Okay. But it is possible that their velocity is, let us say, in some other direction, not exactly in the direction which is like this. Here velocity is in this direction. Instead it is some angle, let us say, or some other angle. Okay. Velocity is in a different direction. So then what will happen? So then what we can say is the velocity will now can be basically split into two components, horizontal and vertical, and means parallel and perpendicular. You can make the velocity into two components, one called parallel component, another called perpendicular component. So we can call velocity of perpendicular component velocity parallel component. So I will just use two lines to make it perpendicular and parallel. Now what happens to this perpendicular component? Perpendicular component behaves exactly like this. So you can substitute the perpendicular component into this and calculate the value of r. So you will get the value of r. Now what about the parallel component? So the one which is parallel to B, that is in the same direction as B, one which is parallel to B, either in the same direction or the anti-parallel direction. In either way, when it is parallel to B, sin theta basically sin 0, hence it is basically no force being applied. There is no force. F magnetic is 0 because of that. Hence what happens is that particular velocity will continue to remain as it is, that does not change, no change in velocity. Now think about this. Now what is happening is that this has two components of velocity. One component will make sure that this will go around here. So see, you started only to go in this direction, but this magnetic field made you go around this, remember this. Okay, you are not going around this in the first place, you are just trying to go straight. This magnetic field made you go around like this. Now when you made it go around, instead of going in the perpendicular V, if you go in some other angle, then it does two things. One, the perpendicular component makes it go around, and the parallel component makes it move in the direction of that. Parallel component makes it move. So there is actually a circular movement, okay, and there is also a movement like this or inside the board. So put together we call it as actually a helical movement. And if you want to watch what a helical movement is, you can see here. So if you start with basically x, y, z coordinate system, this is x, y and z, okay, and in the x direction we have actually B, you can see, okay, and in the y direction the charged particle, okay, is having a velocity component, velocity which is not exactly perpendicular to B. The velocity of this is not exactly perpendicular to B. So if you can actually split that into two parts, one perpendicular to B, one parallel to B. The one perpendicular to B, that this one, will make sure this charged particle will go around the x axis. At the same time, one which is parallel to B will make sure that the charged particle also moves from left to right. So now the two things are happening. Charged particle is moving from left to right and is also moving around the x axis. Both these simultaneously, when you make that happen, it will create an helix. This is called a helix. Helical movement. This is called helical movement. So you may be asked many times to find out whenever when given a value of V, okay, can you find out using your methods what you have, what is the radius of the helix and what is the pitch of the helix? What is the radius of the helix and what is the pitch of the helix? That is the question. Okay. Radius of the helix is easy to find out. We have already found out. Radius of the helix is this. So we can say radius of the helix actually equal to m into V perpendicular divided by QB over. That is the radius of the helix. Now what is the pitch of the helix? Assume that helix actually, if in one, we want to find out in one round, okay, by the time it takes one round, how far it has gone. That is called pitch. The distance between these, each one of those. Okay. Every round, one round, within one round, how much time, how much fast it has, how much distance it has moved. So, if you know the time of one round, okay, then if you multiply it with the velocity, that means basically we can say the pitch p is actually equal to t into v per parallel. T into v parallel. T is one round. To go one round, that is the t. That is already given here, which is nothing but 2 pi m by qb into v parallel. This is our pitch. If you are asked to derive expression for pitch and radius, it's very straightforward. The moment you can derive these two things, this can be substituted here, and you got the pitch of the helix. Now, let's do one simple question, okay, one problem, and then move forward. The question is this. Okay, write down the question. A simple question. What is the radius of the path of an electron? What is the radius of the path of an electron whose mass is 9 into 10 to the power of minus 31 kg, whose mass is 9 into 10 to the power of minus 31 kg, so we are asked to find out the radius, how much, okay, and charge 1.6 into 10 to the power of minus 19 coulombs. We always know that charge of this is 1.6 into 10 to the power of minus 19 coulombs. Moving at a speed of 3 into 10 to the power of 7 meters per second. Moving at a speed of 3 into 10 to the power of 7 meters per second. In a magnetic field of 6 into 10 to the power of minus 4 Tesla. In a magnetic field of 6 into 10 power minus 4 Tesla. Perpendicular to it. We have been told that it is perpendicular to it. What is its frequency? We have to find out what is its frequency also. What is the new value? These are the questions. Okay, and it is also asked find the energy in kilo electron volts. Energy, okay, called energy in kilo electron volt is equal to how much? They have also given us the conversion factor from joule to electron volts. 1 electron volt is equal to 1.6 into 10 power minus 19 joules. So you can clearly see here, when you do this kind of a problem, this is not a very complex problem. Okay, you just have to you will get an idea, get some idea about what are the values. Okay, how do they look like, and you also get to know some of the constants, what their real values are, how to use them, all that. So it's a simple problem though. So you can say R is equal to, formula is there, R is equal to mv by q into b. So you can substitute, m is 9 into 10 power minus 31, v is 3 into 10 power 7. You can see here t 10 power 7, it's almost like 3 into 10 power 8 would have been velocity of light. So nothing can go faster than that. This is 1/10 of that. 3 into 10 power 7 is 1/10 of the velocity of light, divided by q is 1.6 into 10 power minus 19, and b is 6 into 10 power minus 4. So you can compute it, and you will get the value as about 28 centimeters, 26 centimeters. So ultimately it will give you a circle of 26 centimeters radius if you have all these values. Okay, so that's how you can calculate the radius, and you can calculate frequency also. New formula is there, is nothing but qb divided by 2 pi m. Okay, r you can even simply write it in terms of 2 pi r, v by 2 pi r. So we know the v, so we can calculate directly v by 2 pi r. That is the velocity is given to you. Okay. So if you calculate that, you will get basically it has about 2 megahertz. So that is the speed with which it is actually going. I mean, 2 million cycles it is doing in 1 second. So fast it is actually going around. And then energy will see. Energy is nothing but half mv square. Okay. So half into mv square, velocity is given to you, so you can calculate. So that will come to somewhere around 40.5 into 10 power minus 12 joules. But you can actually convert that and you will get 2.5 kilo electron volts. You can calculate this. So this is basically how you can simply compute in a if a charged particle is moving, the kind of path it traces in a magnetic field. Whenever you take a charged particle and try to throw it in a magnetic field, it will never go straight. It will take a circle. It will become a circle. That is the beauty of the interaction between a magnetic field and moving electric charge. Anytime you just shoot a charge into a magnetic field perpendicular to it, if you put a V perpendicular to it, and start taking a round like this, and that round will basically be having a radius r, for which you can simply calculate mv divided by qb as the radius. Okay. So this is one idea you have got, and now we will use this idea in 2 or 3 scenarios. First one we were talking about is in the nature, how does it look like? Okay, we will talk about its basically appearances in nature, how it looks like. Okay, and then we will look at what we call cyclotron to accelerate the charged particles. How do we use it? So this is one of the very interesting things that you see when you go to Earth's poles. Now, if you go to either North Pole or South Pole, you will be actually able to see very colorful sky. Okay. So something like this pink and green kind of a colors that you can see in the sky, forming what we call Aurora Borealis. And you can actually search for Aurora Borealis in Google, and you can see actually many different very interesting and nice pictures of Aurora Borealis. So earlier people were not knowing how these things get formed in the sky, when mostly why it happens only in polar regions. So later there was a theory that developed, and then they tested and found out the main reason for that is the movement of charged particles. So how does it happen? Let's just understand a little bit Aurora Borealis. So what happens really is Earth has this magnetic field, and see, look at Earth, and like a bar magnet, Earth also has its magnetic field. Okay, and it so happens that whenever certain charged particles are emitted from sun, okay, with some solar flares up, sometimes sun flares up and sends out some kind of electrons and protons thrown into the whole of the space around, and it will also reach Earth. So when it reaches Earth, when it comes to the Earth, when they are really traveling, these things are really traveling, the charged particles, and those charged particles are traveling in Earth's magnetic field. Okay. So when they are traveling in the Earth's magnetic field, you can look at their velocity. They may not be exactly perpendicular to the Earth's magnetic field. Every point of time, every point in space, this is the Earth's magnetic field. If it is exactly perpendicular, the velocity of that in the Earth's magnetic field, then it will only bend it. Okay. So, but however, when it is not perpendicular, it is some other angle, then it will not only bend it, make it go in a circle, but it will also make sure that it will continue to go along the B also. So actually it forms some kind of a helix. These things form some kind of, see, look at this, form some kind of a helix around this. They form helix around this, like this. So these charged particles will keep moving around these field lines like helix. This is what they are showing here. And it so happens that we know very well that in any kind of a magnet, the magnetic field strength is highest near the poles. So it is very dim here, but it is very strong near the poles. So hence what happens is that all these coming from various points, they all basically combine together near the poles. You can see the density of these particles near the poles, the particles which were actually sent by the sun. So those particles are very, very heavy. A lot of such particles are there near the poles. Okay, and these particles, what they do is they don't simply move. So if they simply move, if there is no atmosphere, we couldn't have found anything. However, if you actually see that the atmosphere has got oxygen and nitrogen, and the oxygen actually gets excited, both oxygen and nitrogen, both of them get excited by these charges hitting them. So when they get excited means the electrons go up the shells, okay, and when they again de-escalate and come back, they emit certain light. Okay, one of them, oxygen, emits actually green light and nitrogen emit pink light. So those green and pink light put together finally will give you that kind of a colors. So look at this. This is such a complex phenomena to explain this Aurora Borealis. You have to understand the movement of charged particles in the magnetic field, and those, where are those particles coming from? You have to show that they are coming from the sun. And why are they going to the poles? Because of the Earth's magnetic field. And they are themselves not doing anything. They are hitting all the oxygen atoms and nitrogen molecules and oxygen molecules and make sure they excite them. And when they excite them, they come back and they give up pink light and green light. That is when you see Aurora Borealis. So if somebody asks you to explain Aurora Borealis, you should be able to do whole of this, every step of this. Okay. So that is basically our moving charges in magnetic, in a magnetic field. Okay, how the charges move. So now we will see, this is what we have shown here is a natural occurrence. Now we are going to see whatever we are going to make out of it. So let us take a scenario of something called as a cyclotron. Cyclotron is a very interesting equipment. Okay, you can see. Look at the cyclotron. Okay. This is like a huge circular thing. Okay, and there is a cavity inside. Inside that cavity, what we do is we actually send out some charged particles. Okay, and those charged particles will actually start from the center and keep rotating like this inside. And as they rotate, they are made to speed up. They are made to accelerate. So as they accelerate, they come more and more near to the end of the periphery of the circle. And when they do that, ultimately they go out by using a deflector. And when they go out, they will be accelerated. So the cyclotrons are simply some kind of a particle accelerators. Particles start from the center, starts going around like this, and as they move towards the end, they get to become very high speed and they go away. That is called a cyclotron. So a cyclotron is simply a particle accelerator where we use electric and magnetic fields to accelerate the charged particle from the center towards the periphery of the circle, which will go away. Okay. Now let us see how it works. So it works in a let's look at some kind of schematic on how it works. The first thing that we do is that on the top and on the bottom, okay, we put very powerful electromagnets. So these are electromagnets, top and the bottom. So which will make sure that there is an magnetic field. So these are electromagnetic, means it produces magnets. So there is a magnetic field in this direction. Okay, there is a magnetic field in that direction. So from top to bottom or bottom to top, that is the magnetic field. And in the middle, you can see very clearly that there is a cavity. There is a cavity, a disc kind of a thing is, and there is a cavity. A disc is a slightly peculiar disc, okay, in the sense that it is not a full complete disc. It is a disc which is split into two parts. Okay, there are two halves of the disc, slightly separated. You can see two halves of the disc slightly separated, hollow discs. Okay, so these each one of them are called D. Okay, it looks like a D, or we can say D's. Two D's are there. They say they are D's. These two are called D's, two semicircular ones. So what happens inside that? Let us see that. Okay. Now I am going to basically not worry about the top and bottom and only expand the middle one, which is the two D's. Okay. So let's look at the two D's. These are called D's. Okay. So now this is a semicircular one. You can see cavity inside. Now from top to bottom or bottom to top, in this case actually top to bottom there is magnetic field. Okay. Now what will happen is in the middle you can see that you leave a electron, okay, one electron, and that electron will start basically rotating like this. Why does it start rotating like that? Well, the moment the electron has not only electron, I mean any charged particle, the moment the charged particle has a velocity, okay, this magnetic field which is there like this will bend it. Okay. When the magnetic field bends it, it basically gives a perpendicular force. It will make it go in a circle. Okay. So it will actually go in a circle. Okay. So this circle, same circle, it would have completely keep on going, okay, without actually expanding. But we are doing something else. If we just use the same circle, okay, it will keep on going. But we are doing something else. What we are doing is, whenever it goes from one D to the other D, okay, between these two D's actually we have applied a nice electric field. We have applied electric field with two D's. That means whenever it is going from, so not other areas, in all the other areas it is completely shielded from electric field. Only here, when it is not inside the D's, when they are outside this D and before going to this D, in this small area, it will be basically speeded up by applying certain E, electric field. So it is applied in such a way that the charged particle is in this, let us say it is going in this round. Okay. So if the charged particle is here, then we are giving a E in this direction and speed it up. When the charged particle comes down here, then we will give E in the opposite direction and speed it up. And when again it goes back here, we give the E in this direction and speed it up. So we keep continuing this, which means that we have to give electric field once in this direction, once in this direction, once in this direction, once in that direction. So to be able to do that, we connect an alternate current generator, alternate voltage source, AC, to that, and it adjusts its frequency such that exactly the time it takes from here to here, it switches over to the other side. So how are we able to do that? So that is the beauty of the cyclotron. Okay. Beauty of the cyclotron comes from the fact that whatever may be the velocity of this, so whenever it speeds up, you can see here, the moment it speeds up, its velocity increases, and you may think that it will actually reach here faster, but it doesn't. The reason is that it will now go through a slightly bigger circle and it will take the same time to reach there. So that is what we talked about here. We see that radius is proportional to V, whereas the time period is not related to V. Whatever may be the velocity, it will still reach the other side at T by 2. Again T by 2 here, T by 2 here, like that. Only its radius is increasing and increasing. Every time you increase the velocity, its radius is increasing. That is all. And that makes it basically possible for you to speed it up. Remember this. What we are doing here is that we are utilizing the fact that the frequency or time period of this rotation of this circular motion of these charges is constant irrespective of the velocity. Hence, we can actually provide a simple alternative voltage here. Like, the moment you calculate the what we call cyclotron frequency, calculate the cyclotron frequency by giving value of B and all these things. Once you know the frequency, it is constant. So nothing to change. So cyclotron frequency makes sure that it is fixed at that frequency. Okay. So you know that value, and then you can tune it, tune the E such that its frequency is exactly matching that. So B's frequency and E's frequency are matching, alternating frequency. So not B's frequency, I am saying the frequency of the cyclotron is matching with that. That is called a resonance condition. Okay. When that happens, naturally it gets speeded up. So let's just see how much it gets speeded up. Okay. So this is a normal simple diagram that you can write when you are explaining this. So these are all dots. You can see these are all the dots. This means that all the magnetic field is coming like this way, like this magnetic field. Okay. Now magnetic field, we have put a top view of that. Okay. Magnetic field coming this way. Now on the D you can see that this is the path. So you start from here. It moves like this and goes away outside, and this oscillator gives that frequency. Okay. You can calculate what is the value of the this is called cyclotron frequency. How do you calculate? You already have it, Q into B divided by 2 pi m. Depending on what the ion that you are using, you have the value of Q and M for that. Q by M you will know, and depending on the value of B that you are given, you can calculate the cyclotron frequency. Now you adjust the E such that E also does the same frequency, and phase should be correct. Actually, you should not do in such a way that frequency is same, but whenever you go here you decelerate it. That should not happen. Every time it has to properly accelerate. Okay. It should be in the correct direction. So what you do then is you calculate the value of R. If you see radius at any point of time, if you want to find out the radius, that would be equal to mv divided by qb. Correct? So velocity at any point you can write it as r into qb divided by m. That is the velocity at any point. Now when you take, for example, this whole of this has a maximum radius of r. Okay. So if there is a maximum radius of r, then maximum velocity v at exit, whenever it comes out of this, that is the maximum radius. At that time it is qb into capital R by m. That will be the velocity. You can calculate the velocity to which it gets accelerated. It will be simply dependent on b and capital R. Q by m is basically a characteristic of the charged particle that you have. So this is basically how you can use a cyclotron. Cyclotron, when you want to talk about a cyclotron is all about calculating the exact cyclotron frequency and adjusting the E such that E oscillates at that frequency. And the oscillator is to be oscillated at that frequency. And also you can calculate the energy of the cyclotron, half mv square. So by looking at what is coming out here, okay. So this is basically V exit. So we can say half into m into exit q b r m whole square, which is nothing but q square b square r square by 2m. This is nothing but the kinetic energy of the molecule of the ion that is coming out of a cyclotron. So if you are asked to find out what is the kinetic energy of the charged particle that is coming out of a cyclotron, this is what it is. Yeah, it's very straightforward, nothing to do, not too much of work. Okay. So this is basically our what we call a cyclotron. It's very used in many cases. Most of the particle accelerators, wherever you want to accelerate a charged particle, the cyclotrons are actually used. Okay. Now I'm going to show you one more application of this moving charges. One more application. So the application is called as velocity selector. What is a velocity selector? So let us say there are a lot of charged particles which are coming through a certain tube. Okay. Now what I want to do is I want to basically take out those particles which have a known velocity, which has a velocity that I know of, in the sense that I'm going to basically put lots of different kinds of particles are there. That's lots of particles. Okay, so they are all going in this direction, some direction. Now I want to make sure that only certain particles having certain velocities, exactly those range of velocities, I want to select and take out those particles. This is required in so-called mass spectroscopy and all that, where looking at the mass you can actually split the particles. All the protons go this way, all the new electrons, neutrons go this way. Neutrons and all you cannot even deflect otherwise. Okay, so there's some kind of a velocity selector for the charged particles. How do we do that? Okay, not for the neutron, for the charged particles. Okay. So what we do is we use a simple technique for the charged particles. So we know that F is equal to F electric plus F magnetic. Okay, so F electric is Q into E plus F magnetic is Q into V cross B. You know this. Okay. Now if we suppose consider that all these three Q, V and B are perpendicular. Let Q, comma V and B are perpendicular to each other. If they are perpendicular to each other, we can write them in the XYZ coordinate system. If you see, actually, you can write down like this. Like this. Okay. So we are going to write this as X, Y and Z coordinate system. Okay. So in X coordinate system we will put it as V is in this direction, and we will also make sure that our E is in this direction and B is in this direction. So mutual perpendicular directions. So let's just write them in the format that we understand. Okay, V can be written as magnitude V into I cap. I'm just writing in the vector format, and let's say E is written as magnitude is E into J cap. So in Y direction is J cap. So similarly B can be written as magnitude B into K cap. So now let's substitute this here into this equation. Okay. So F is equal to Q into E is nothing but what? E J cap plus Q into V cross B. So V cross B is nothing but V into I cap cross B into K cap. So we know that I cross K is actually minus J. Okay, I cross K is minus J. Think about it. Okay, Q into this is nothing but Ej cap plus this is Vb, I cross j is minus j, which is nothing but q into E minus Vb into j cap. You can see that always F force, whatever we are talking about, is q into E minus Vb. Okay. The net force works like this. You have your force, which is basically electric force, is like Fe is like this. Okay. And you also have the Fm, magnetic force, is like this, Fm. And if these two happen to be equal, then this particular V, this particular charge will keep on moving like this straight without bending. Okay. So now what is that value? You can see what is our scenario? E must be equal to Vb. So for E is equal to E minus Vb is equal to 0, or E is equal to Vb, or V is equal to E by V, for this velocity, okay, for that velocity there is no bend, in the sense that for only one particular velocity, if the velocity is any different, okay, then it will either Fe will be more, or Fm will be more, and it will actually either bend this way or bend that way and go. Okay. So only when the scenario one particular value of E by B ratio, okay, will suit this velocity, and hence it is called as velocity selector. So what we do is, whenever some things are flowing through a tube, let us say, and you want to select one particular velocity, all the particles moving in that velocity, I want it to proceed in the direction, and all the remaining I want them to go away here and there. So what do? I now find out what is that velocity, whatever we want. We create electric and field and magnetic field whose ratio is equal to that velocity. The moment that happens, then you can see that they are actually going in the straight line, and you can choose only those particles and select them. So this is velocity based selection of the particles. So if you are asked to write down about the velocity selector, you have to go through this principle basically, and then talk about how do you select the velocity. Please try to think about it, understand and write. So you will get a good understanding of, you will know basically the uses of these things. Okay. Now we have discussed in this session more about the various kinds of movements of charged particles inside the magnetic field, and we saw that generally if the velocity is perpendicular to B, it always can trace a circle. Okay. And then we found out the radius of circle and frequency of rotation and all that. Then we used that to see what will happen when there is actually a velocity which is not really perpendicular but some other direction. Then we saw that it will form a helix, and we saw that helical movement is there in Aurora Borealis, where we have seen how a nice colored Aurora Borealis is seen in the polar region. Then we saw how to utilize this constant frequency, irrespective of the velocity, how it takes the same amount of time to go around. So we use that as an accelerator and accelerated that in cyclotron. And then we also used the fact that these two can be opposite direction, Fe and Fm, and use it as a velocity selector and choose whichever particle you want. So these are the many techniques you use when you are working with the atomic physics and nuclear physics. So if you know these techniques, you can basically find out ways and means of selecting and separating the charged particles, different mass particles, mass spectroscopy, all those areas. Okay. So in the next session, we shall basically work on what happens if you have a conductor carrying current, what will be the magnetic field because of the current. Till now we are seeing what will happen to the conductor in the magnetic field. Now later we will see what will happen to the magnetic field in the presence of a conductor carrying current in the next session. Bye.